The term software-defined vehicle, SDV, has become a central concept in automotive transformation. However, its definition remains controversial and fluid. Over the past decade, industry consortia and alliances have worked to implement SDV principles, navigating a landscape of complex software stacks, heterogeneous operating systems, and strict safety and security requirements. Unlike other industries that have transitioned more smoothly to software-defined paradigm, the automotive sector faces unique challenges, ranging from real-time constraints, functional safety, and cybersecurity regulations, and long development and validation cycles to heterogeneous and legacy hardware, limited compute and power budgets, and need for cost-effective scalability across diverse vehicle models and tiers. This talk explores the evolving meaning of SDV and outlines the path forward, highlighting emerging enablers such as cooperative driving, cellular vehicle to everything CV2X, and cloud-native vehicle architectures. These advancements point forward a future where vehicles act as a dynamic, connected computing platforms within a broader mobility. Good morning, afternoon, evening, everyone. Today, we dive into the future of automotive technology, where the convergence of software-defined vehicles, cellular V2X, and multi-access edge computing under a unified cloud-native architecture is preparing the way for the transformation. Cloud-native paradigm applied for the SDV will change the landscape of connected and autonomous vehicles and drive innovation towards safer, more efficient transportation systems. My name is Andrei Kholodnyi, and I'm a principal technologist in the office of the CTO. I'm responsible for leading the technology strategy for next-generation software-defined vehicles, CV2X, cloud robotics, and edge embedded systems. My main activities in this role include creating proof of concepts and prototypes to validate innovative technologies, as well as contributing to external-facing CTO activities, such as speaking engagements, writing white papers, and more. Before joining the office of the CTO, I served as a lead software architect where I designed the first Linux-based automotive infotainment system for BMW and developed the first samples of autonomous driving systems. The concept of software-defined vehicle has emerged as a defining theme in the transformation of the automotive industry, promising to revolutionize how vehicles are developed, maintained, and experienced. Despite its growing prominence in marketing technical papers and consortium roadmaps, the term itself remains loosely defined. Stakeholders across the ecosystem, OEMs, Tier 1 suppliers, software vendors, and regulatory bodies interpret SDV differently, often aligning the definition with their strategic priorities and technical constraints. I have gathered a few examples on this slide. For some, SDV is a vision of complete software abstraction from hardware. For others, it is primarily about enabling over-the-air updates or generating new revenue streams through digital features. Some even point out the lack of a shared cross-OEM vision or consistent scope for what SDV truly means. This ambiguity has led to heated discussions, incompatible implementations, and occasional skepticism about whether SDV is a genuine technical direction or just another buzzword. The shift from mechanical to software-driven innovation is real and necessary. Traditional vehicles were differentiated by engine performance, handling, and design. Today, competitive advantages increasingly come from software-defined features, advanced driver assistant, infotainment systems, energy management, and connectivity. In this context, SDV represents a natural evolution that touches every layer of the vehicle architecture and the supply chain. SDV is a term loaded with ambition, but lacking a single canonical interpretation. Understanding this ambiguity is essential to navigate the real progress being made and the roadblocks that still remain. Let us take a closer look how WindRiver and Aptiv define it. WindRiver's vision for software-defined vehicle focuses on delivering comprehensive cloud-native and edge-driven platform that enables automotive manufacturers to develop, deploy, and manage software throughout the vehicle's lifecycle. We emphasize this shift from traditional hardware-based ECUs to highly integrated, virtualized software platforms supporting both safety-critical and non-critical applications. WindRiver's solution incorporates CI/CD automation, thorough testing, and real-time analytics, ensuring faster time to market and continuous software updates. Our platforms also prioritize safety, security, and modularity, supporting mixed-criticality systems over their update and robust software development workflows. Aptiv defines the software vehicle as a vehicle those features and functions are primarily enabled through software, making a shift from hardware-centric vehicles to software-driven systems. Aptiv highlights several benefits of SDV, including the ability for over-the-air updates that can enhance safety performance and user experience. The company emphasizes the need for agile development practices with the separation of software and hardware development and move towards modular service-oriented architecture. For more information, please use links I have provided at the bottom of the slide. First coined around 2015, the term software-defined vehicle represents a shift in the automotive industry towards vehicles where software plays a central role in management functionality and user experience. This concept quickly gained traction, promises transformative changes in vehicle technology and ownership. In the early stages, the SDV sparked considerable enthusiasm. By 2021-2022, the automotive industry was buzzing with excitement over SDVs, reaching the peak of inflated expectations. Major automotive manufacturers began investing heavily in developing their own in-house software teams, aiming to create superior CarOS platforms. Recognizing both the potential and the fragmentation in Europe, numerous industrial consortia and alliances have emerged to coordinate efforts and standardize this SDV stack. For the better visibility, I have put them on the Gartner Hype Curve. Initiatives such as Eclipse SDV, Working Group, SOFI, AUTOSAR Adaptive Platform, and Calvisa are working to define reference architectures, data models, and software abstraction to make SDVs a reality. However, even these groups do not always agree on the boundaries of the SDV concept. Some focus on cloud integration and edge orchestration, while others are grounded in embedded safety or real-time system guarantees. As a result, the SDV narrative continues to evolve, converging slowly through overlapping initiatives, but still reflecting a diversity of technical and business agendas. Meanwhile, most OEMs are developing their own CarOS, each at the different stage of progress. The evolution of E-architecture and the rise of SDVs are deeply interconnected, with each influencing the development of the other in a continuous feedback loop. Independent ECUs in the 1990s involved isolated functional specific features like one ECU, one feature. In this phase, software-driven functions were limited and hardware constraints drove the separation of systems. The SDV concept was not yet a priority and the vehicle functions were largely hardware dependent. As vehicle systems grew more complex, ECUs began collaborating within domains. For instance, body, chassis, powertrain. This shift helped streamline the integration of various vehicle functions, but SDV principles like dynamic software updates were still constrained by hardware dependencies. With the introduction of central gateway, different vehicle functions started connecting via a unified network. This facilitated the cross-function communication needed for complex tasks like adaptive cruise control. Here, e-architecture changes were driven by the need to support more complex SDV features like real-time data process and over-the-air update. The evolution towards central domain controllers began consolidating functions and reducing costs. This move aligns with SDV goals as software-driven platforms require a more unified architecture to manage increasingly sophisticated tasks. SDV pushes for this change as centralized computing provides the flexibility to update software features and scale them across multiple vehicle models. With zonal computing power is moving closer to sensors and devices. This shift enhances SDV capabilities by improving scalability and reducing cabling. The need for real-time dynamic software features and SDVs accelerates the transition towards zonal architectures. And the final phase, as we know today, is characterized by high-performance computing in virtual domains, with Ethernet-based communication enabling efficient data flows between vehicle systems. SDV will drive this transition at the vast amount of data needed for autonomous driving, AI, and advanced safety features require powerful computing infrastructure. E-architecture's innovations enable SDVs, but the requirements of these vehicles also shape the next generation of EE design. Which comes first? This is a chicken or egg problem. So E-architecture or SDV. In the evolution of E-architecture, SDV requirements often act as a key driver for change. As SDVs demand more computation power, dynamic software capabilities, and real-time processing, E-architectures must evolve to meet these needs. However, the fundamental shift towards more centralized and modular EE systems provides the necessary foundation for SDV to evolve. So, while SDV concepts often catalyze changes, E-architecture must first mature to provide the infrastructure necessary for SDV to operate effectively. And the key milestone in the SDV journey is the shift from distributed E-architecture, where each function relies on a dedicated ECU, to more centralized compute model. This transition reduces complexity, improves efficiency, and enables cross-domain integration. Instead of siloed systems, centralized domain controllers, and eventually a central vehicle computer or vehicle brain allow functions to be abstracted into software layers. This not only supports dynamic updates and shared computing resources, but also aligns with the SDV vision of treating the vehicle as a scalable digital platform. In a domain-based E-architecture, each domain compute unit is responsible for a major vehicle function, such as body, powertrain, ADAS, infotainment, or connectivity, and typically runs its own operating system tailored to its performance, safety, and real-time requirements. For example, the ADAS domain often uses a heterogeneous architecture combining high-performance CPUs, GPUs, and accelerators, running multiple OSs like Linux, real-time operating systems in parallel. The most compute-intensive domains, ADAS, infotainment, and connectivity, drive the adoption of powerful hardware, virtualization, and service-oriented software stacks that are foundational for software-defined vehicle vision. Domain architecture, however, Zonal architecture on the left marks a key evolution in the SDV journey by restructuring hardware layout for efficiency while maintaining some domain separation. In this model, zonal ECUs are placed close to sensors and actuators, aggregating data and significantly reducing cabling complexity and vehicle weight. Each zone has own compute unit and OS, enabling localized processing and communication with centralized functions. While high-performance domains like connectivity, ADAS, and infotainment often retain dedicated compute units, Zonal ECU supports data pre-processing, real-time control, and network management. This enables scalable integration into more centralized SDV architecture, where a central brain, a powerful compute platform, begins orchestrating software-defined features across zones and domains. Zonal architecture is thus a bridge between legacy domain models and full SDV centralization, enabling modularity, upgradability, and service orchestration in more efficient hardware layouts. The central brain architecture on the right represents the most advanced stage in the SDV evolution. In this model, all major domain ECUs, ADAS, infotainment, powertrain, body, and connectivity are integrated into single high-performance compute unit, often called the central brain unit or central computer. This central brain runs multiple virtualized or containerized OS instances, orchestrates services across the entire vehicle, and enables cross-domain functionality, dynamic feature updates, and centralized safety and security enforcement. Supporting this central unit are zonal ECUs, which is similar to the zonal brain architecture, distributed across the vehicle to handle I/O aggregation, low latency, local control, and pre-processing close to sensors and actuators. This zonal ECUs communicates with the central brain over high-speed Ethernet, creating a scalable, service-oriented SDV platform. The central brain architecture is a key enabler of the software-defined vehicle because it fundamentally shifts the vehicle from a collection of siloed embedded systems to unified programmable platform. This architecture creates the groundwork for cloud-native vehicles, enabling faster development cycles, new digital business models like features on demand, and seamless integration into the broader digital ecosystem. Here is an example of zonal architecture from BMW. BMW Neue Klasse marks a significant shift towards a truly software-defined vehicle. Unlike past models, where development restarted with each new generation, Neue Klasse enables continuous software development, ensuring faster iterations and long-term feature evolution. Some highlights: 4 central computing units, superbrains. These specialized compute nodes form the backbone of BMW's SDV approach, handling specific functional domains. Driving dynamics, heart of joy. BMW's first full in-house system integrates motor and chassis control, delivering 10 times faster performance than current models. Automated driving, a dedicated unit for driver assistance and autonomous functions with 20 times the computing power more, enabling advanced perception and decision making. Infotainment, panoramic iDrive, powered by BMW OS X. It manages the digital cockpit, voice interaction, navigation, and user personalization. Core vehicle functions centralizes systems like lightings, climate control, and access control, integrating up to 100 individual functions into a unified control layer. It has also zonal wiring architecture. BMW shifts from traditional distributed to a zonal structure, significantly reducing complexity. 600 meters less wiring, 30% weight reduction, improved scalability and software manageability. And Neue Klasse vehicles boost over 20 times the computing power of current BMW generations, laying the groundwork for real-time updates, predictive systems, and AI integration. Software defined by design, so the entire platform is built to support continuous software updates, enabling long-term evolution of feature services and driving experience through over-the-air updates. BMW said that they have invested in a global software network with 10,000 IT and software experts, working with over 1,000 software modules and 500 millions, you can just imagine, 500 millions lines of code. BMW CodeCraft cloud-based development platform supports up to 75,000 virtual CPUs and process 200 software builds per day, reflecting an increasing reliance on AI assisted software development. We are actually at the important point across all industries, shifting from hardware-centric models to software-defined systems. This transformation is not just about adding software, but about fundamentally changing how values are created, delivered, and sustained. In industries like consumer electronics and enterprise IT, this shift has already happened. Software-defined infrastructure is the norm. In telecom, the transition is a full swing as 5G pushes intelligence to the edge with multi-access computing, Open RAN, etc. Aerospace and defense are deploying next-generation hardware with advanced software stacks already in production. And in automotive, we are actively developing software-defined vehicles with prototypes and early production models beginning to reshape the vehicle lifecycle. The move towards software-defined architecture is driven by three major enablers. And you can see them on the right side. So it's app integration. We are collapsing fragmented siloed systems into centralized compute platforms. Instead of dozens of isolated CPUs or ECUs, we now see domain controllers or even centralized vehicle brains. This not only reduces costs and complexity, but also enables richer cross-functional features. Second is virtualization. We abstract in software from hardware. This means functions are not longer hardwired to specific chips. Software can be updated, swapped, or scaled without replacing hardware, just like in the cloud computing. And third is artificial intelligence. As vehicles collect more data, AI becomes the key to turning data into actionable insights. Whether it's personalizing the driver experience or predicting component failures, AI is becoming fundamental to how modern vehicle operates. But as we make this transition, we must maintain the automotive pillars: safety, security, and reliability. This is the essence of software-defined transformation, unlocking agility and innovation while never compromising the mission-critical nature of the system. As we transition into software-defined world, the role of the intelligent edge becomes increasingly critical. Data is no longer only processed in the cloud. Intelligence is being distributed across the entire ecosystem, from sensors to centralized compute and even to regional data centers. Let's break this down across three main layers of the edge. First, the far edge. This is where data is generated. At the device edge, sensors like cameras, radars, or lidars in a vehicle start collecting raw data. Then, at the infrastructure edge, this data travels through in-vehicle wiring to local compute units like ADAS domain controllers or infotainment systems that must act in real time to support functions like emergency braking or driver assistance. Next is the near edge or the metro edge. This layer represents regional aggregation points, like points of presence where data from multiple vehicles is transmitted via 4G or 5G. These metro edge nodes allowed for real-time traffic analysis, fleet management, and rapid over-the-air updates closer to where the vehicle actually operates. Finally, we reach the cloud, where deep learning, long-term storage, fleet-wide analytics, and model training take place. Data from vehicles is pushed through the metro edge into centralized cloud platforms over high-speed fiber. This is where strategic insights are developed, from improving software performance to enabling predictive maintenance and next generation autonomy. And this pattern isn't unique to automotive. Every industry is moving towards this edge intelligence model. In consumer, far edge is your smartphone camera, and in telecom, the radio units is the far edge, and the base station acts as the infrastructure edge. In aerospace and defense, a radar on a jet is the device edge, and plane mission system acting as the compute infrastructure. And in automotive, the radar is the far edge, while the vehicle high-performance compute, car track, forms the infrastructure edge. This shift from cloud-only thinking to distributed intelligence is unlocking new opportunities for latency-sensitive applications, real-time decision-making, and more resilient, scalable digital infrastructure. And software-defined vehicle will evolve rapidly in this edge-enabling world. As we move towards software-defined vehicles, the automotive software architecture is evolving rapidly from a fragmented set of components to an integrated cloud-native software stack. We started with the back-of-PCS approach. Each function has its own ECU, its own tightly coupled software. This creates complexity, redundancy, and made software updates nearly impossible. Each system was isolated. Then came the service-oriented architecture introducing domain controllers and hypervisors, RTOS and Linux systems, managed services using monolithic middleware, a big step forward, enabling better collaboration between ECUs within a domain, but still relatively constrained. Now we are transitioning to a microservices-based architecture. Software is becoming more modular. It brings us closer to how modern software is developed and maintained in cloud-native environments. Looking ahead, the goal is a cloud-native vehicle architecture. We move from domain compute to central compute. Here we see containerized workloads running on RTOS. By the way, VxWorks is the first RTOS which supports containers and Kubernetes. Linux and Android, and all managed on the Kubernetes-like orchestration. This architecture allows for massive scalability, real-time updates, better resource usage, and feature portability, hallmarks of software-defined vehicle. This journey is not just about technology, it is about transforming how we think of cars from static machines to dynamic, evolving digital platforms. This is an example of cloud-native vehicle architecture built to support mixed criticality workloads. A safety hypervisor runs directly on the SoC, handling system partitioning to securely isolate different OS instances, from safety-critical RTOS like VxWorks to non-safety-critical Linux or Android, all running in parallel. Each operating system functions as a cloud node, complete with its own network agents, such as Kubernetes, to ensure its containers are running reliably. The central compute unit hosts the container orchestration engine, effectively running the entire vehicle or converting the entire vehicle into subcloud. This setup requires that all deployed OSs support containers and orchestration agents, which is something our RTOS is fully capable of. One of the key challenges here is enabling a mixed criticality orchestrator capable of managing safety critical and non-safety critical containers differently while keeping them coordinated. The same architectural pattern extends to zonal compute units and embedded sensor control nodes, each also running a mix of RTOS, Linux, and container workloads. At the system level, Starling X runs as the edge or Mac, handling platform management across the entire distributed vehicle cloud. What is the big advantage? Workloads are managed uniformly and can shift seamlessly between in-vehicle compute and the edge without code changes depending on performance or latency needs. Here is an example of how to improve safety, comfort, and convenience through integration with a cloud-native software infrastructure. ADAS systems must react within extremely tight latency budgets, about 250 milliseconds total, with a minimum tolerance for error. That time is consumed across several critical processing stages, like 50 milliseconds for sensor data processing, another 50 milliseconds, for instance, for tracking and object detection, 50 milliseconds to update the environmental model and generate driver assistance decisions, followed by motion planning, and finally vehicle control and CAN transmission, all within a narrow 35 milliseconds window. This where C-V2X integration and cooperative perception comes into play by leveraging infrastructure-based information such as real-time traffic light status and road sensor data. Vehicle can augment their onboard perception. This data is integrated directly into the environmental model, improving accuracy and awareness, especially in scenarios where line of sight is limited. To enable this, network slicing is applied to guarantee the low latency and deterministic communication required for these enhancements, making the entire ADAS pipeline not only faster, but also smarter and more informed. This fusion of in-vehicle intelligence with external sensing infrastructure lead to a significant boost in safety, comfort, and driving convenience, especially in dense urban environments. Let's take a closer look at the key challenges in building a software-defined vehicle. I will not go through the full list, but just we'll name a few of them. First of all, it's cloud-native for heterogeneous mixed critical systems. One major challenge is applying cloud-native principles like containerization and orchestration to a system made of different operating systems, levels of criticality, and distributed compute. We are talking about mixed safety-critical RTOS with Linux and Android in a unified architecture and making sure everything is orchestrated correctly, securely, and predictably. Then safety and security compliance. Any automotive system must meet standards like ISO 26262 for safety and cybersecurity. Achieving this while using dynamic software elements like containers and over-the-air updates introduce significant complexity. Real-time determinism in mixed workloads. Some functions like ADAS or braking require hard real-time behavior, ensuring deterministic performance and virtualized containers environment and not trivial. Then the standardization, so to make it interoperable, SDV systems involve many domains, and it should be harmonizing interfaces and ensuring components work together, and this is essential and difficult. Then the data orchestration across domains must manage data flows between zonal ECUs, central compute, edge, and cloud. And this includes secure real-time data orchestration. And then the last one, scalability and cost efficiency. Automakers need to scale software features across different vehicle lines without exploding costs. The architecture must support reuse and modularity without over-provisioning computer memory. As we wrap up, let's reflect on the key takeaways from today's presentation. Software-defined vehicles are reshaping the automotive landscape by enabling more flexible and scalable systems. The move towards SDVs allows for software-based control over vehicle functionality, enabling ongoing updates, feature enhancements, and better management of mixed criticality workloads. With cloud-native architecture, SDVs are becoming more adaptable to future changes and innovations. This architectural approach allows for seamless software updates, containerization, and better management of system resources. The combination of centralized and zonal computing models ensures that the complex and mixed critical workloads and SDVs are handled effectively. By bringing computation close to sensors and devices while maintaining central control, we can provide both performance and safety. 5G connectivity is a game changer. It enables real-time communication between vehicles, infrastructure, and other connected systems, which is essential for features like cooperative perception, dynamic traffic management, and ADAS. The low latency, high-speed capabilities of 5G allow SDVs to respond to the environment more effectively, improving safety and user experience. And finally, the development of SDVs is not just about building new vehicles, but also about converging IT and OT technologies. That convergence requires cross-domain expertise, especially in cloud, embedded systems, and networking to create a robust vehicle architecture. Thank you all for your attention, and I'm happy to take your questions now.
Nice job, Andrei, as before. We got lots of questions for you, so...
Really? Okay.
Hopefully you're
Let's
ready.
move on.
All right. What key challenges have historically prevented open source platforms like Linux from gaining traction in safety-critical automotive applications? And, part two, what recent developments are helping overcome these barriers?
This is a great question. I think, first of all, the safety requirements, first of all, because if you develop software based on the ISO 26262 standard, you really follow the V process starting from specification, design, and then going to tests, integration, and so on. So Linux as an open source software model is different. So people just developing software. And then it's quite difficult to certify this software because the software is not developed based on the safety principles. And besides of that, if we take into account the size of the Linux kernel, if we are talking about Linux kernel, it's quite expensive to certify it. So this I would say one of the major reasons, and there are consortia which are working on that. So one of these consortia is ALISA. It is on the Linux Foundation. So they pick up the Linux kernel and try to fill these gaps what I have described.
Okay. What are the primary barriers that prevent automotive from achieving the same scale of software-defined deployment as consumer devices?
Well, I think it's first of all is just their very complex hardware and software, right? So because vehicle is quite sophisticated device, and you have so many ECUs, and it's not as I have mentioned in my talk. It's not only about the software, but also to converge E architecture from from this distributed 100 ECUs to consolidated central brain. So this also I would say make things more complex. And of course, as I have mentioned, the safety and security requirements.
Okay. I'm going to paraphrase this one. What's the role of the intelligent edge in real-time decision-making for autonomous and connected vehicles?
Well, as we move forward from from level 0, level 2+, and level 3 of driving autonomy to level 4 and 5, we go from isolated vehicle to cooperative vehicle, cooperative behavior. And of course, we need to exchange then information between vehicles, but not only between vehicles, also between vehicles and infrastructure, which is a road infrastructure in this case. 5G with this matter plays significant role in that, because 5G is their technology which provides real-time and deterministic behavior while exchanging information between the participants.
Okay. What's the role of open source in safety critical automotive environments, and how do initiatives like ELISA play into this with respect to certification?
Well, the open source itself, this initiative in automotive has started in 2007, and I did the first open source Linux project that was an infotainment project for BMW. Since that, there were more and more, let's say, pieces in the software which where open source took over. However, safety is another beast, is another problem for the reasons I have mentioned, and ELISA exactly the community which works on that and try to not only for automotive but for Linux kernel in general, try to fill these gaps. And they have different groups, and one of the group is the automotive group, where they look at Linux certification with regards to ISO 26262 requirements.
Okay. How does the transition from distributed to centralized architectures impact software complexity and system scalability in these vehicles? I like that question.
I think it's not so straightforward. I cannot tell that it will decrease or increase complexity, just because you can imagine it was 100 ECUs, and it was very difficult to support them, right? So each ECU was like one provider, right? So it was quite complex. Probably it was quite simple from the functional point of view, but quite difficult from the maintenance point of view, right? So and it was less functionality. Now automotive OEMs continuously add more and more functionality. Computers become more powerful, and they try to and they start to aggregate all these features on one or a couple of let's say main CPUs. From one side, it makes things more simple, just because you can build everything in one shot, right? So and have it under control. From other side, you start mixing all these various functionalities, which is HMI, ADAS, and so chassis and body domains into one big ECU, and it of course creates some challenges when you start mixing safety and non-safety applications. So it's kind of I would say it's kind of mix between from one side it's simplified, from another side it makes things complicated.
Okay. I don't know if you're going to know this, because we talked about this earlier. Will ISO 8926 play a significant role in certifying open source software, as did ISO 26262?
Say it again. Which one? 80?
where is it? 8926. 8926. I think we talked about this earlier today, and I'm not familiar
right.
with Yeah, okay. All right.
It's ISO, I think, right? So
Yep.
was it ISO?
Yeah, it is.
Okay. Yeah, I know now what people are talking about. So ISO 26262, it is a quite old standard, right? So, and it was really created with their thoughts in mind to develop software based on this V model, right? So starting with design, then produce a software, then test cases, so requirements, traceability, and all these things. So it's very well established process. Now, since people want to, so the technology moves so fast, and it's very difficult to develop software from scratch. So automotive manufacturers try to reuse existing software, but for existing software, this process does not fit very well because it is written, so no requirements, no traceability, and so on. That's why there is another standard which is now on the work where a standardization body tries to define how to manage from the safety point of view this already written software. Yeah, so we will see how it will go. So it's under development.
Okay. This one's more of a discussion than a question, but we see many OEMs giving up control of the software. What's the effect that this has on the software-defined vehicle approach? I'm not sure if I agree with that, but that's the question.
Mm-hmm. Yeah, so I think it's very important point from the automotive OEM's point of view, right? So because when they gain control on the software, they can easily, let's say, design it and modify it in the proper way they like, right? So because in the past, when they handle this only as a hardware, as a black box, let's say, so ECU and the hardware and the software which comes with this ECU, sometimes it was very difficult to apply any modifications, new features, and whatever. And with this, let's say, digital transformation, which all OEM companies now, automotive OEM companies go through, where they have more and more control on the software which goes into their cars, they definitely win.
Okay. I think this is going to be the last one here. How does processing data at different points along the edge cloud continuum impact latency, bandwidth use, and decision-making speed?
I think if everything processed in the vehicle, I mean, it's quite easy to calculate, right? So and to have it under control. But the reality is that it will, so everything get more and more features in the car, and it goes to the outside world, and car now is connected, and now it is an interaction between car and the edge, and there definitely the one of the issues, thoroughly manage and measure and put under control all these timing and latency requirements which arise between the car and the infrastructure. I think it's very depends on the use cases. For instance, for infotainment, it's quite okay to have it somewhere at the edge and then play back from the edge, right? So for ADAS is just another situation where not only real-time requirements and data processing, where the data will be processed, but also like safety and security consideration needs to be taken into account.
Well, thank you very much, Andrei. Awesome session to wrap up our day at the Automotive Technologies Virtual Conference. Again, I want to thank our sponsor, Wind River. I want to thank Andrei for doing double duty here. Both of these sessions were great. And thank you for everyone in the audience for attending and making this a successful event. So have a great day, everybody.
Thank you very much. It was a pleasure to be here.